Hi there, welcome back to Weather Analysis with Mr. CB. Lesson 5 today. So, let's start out by talking again about reminding ourselves the steps of how geostrophic wind works. If you saw the last lesson, you might have seen that kind of strange representation that I made. But if you remember, I was walking towards a railroad track, which that railroad track was supposed to represent an isobar. And for the geostrophic wind situation, if you remember, I ended up parallel to it. And how does that happen again? Um, Once again, that's only going to be able to happen in the upper levels of the atmosphere, and that's the reason that's the reason of that is because there's no friction up there. If there is friction, that makes the wind weaker, and a weaker wind, lower speed, is going to make the Coriolis effect weaker. And if that's weaker, then it's no longer in balance. So that's why it doesn't work at the surface. And that's ageostrophic. Yeah, ageostrophic. But at the upper levels, we're not going to have friction really. So the steps are that in the first place, if you remember, winds always want to go from high to low pressure. And the pressure gradient force is what makes that happen, right? Well, we also have the Coriolis force because the Earth is rotating. And it's like, too bad, deflect to the right. Now that's in the northern hemisphere, okay? Be careful about that. Only in the northern hemisphere. In the southern hemisphere, it deflects to the left. But northern hemisphere is what we care about for weather anyways, because we're talking about United States weather. But anyways, so the Coriolis effect is going to make it go to the right. And then when they are in combination, eventually over time, they end up parallel to the isobars. Um, Now let's talk about a different force that we haven't really yet talked about. I mentioned it a little bit in the last video. That's the centrifugal force. That's not the same thing as centripetal, by the way, but centripetal isn't really something that we think about. You might talk about that in physics, but that's not what we're going to be focusing on. We'll talk about the centrifugal force. Now, a good way to explain this, I already talked about this, I think, in a different video, but in more detail, I'm going to talk about something that happened to me on this day, January 26th, 2024. Well, that was not a super good day to me. Now, something that happened, well, I at that time was playing in this jazz band, and my keyboard was in a place called Beckley, West Virginia. And that was basically 2 hours away from where I was or where I needed to be. So I had to go there to get it. Well, unfortunately, there was very short notice of this gig, and I only was able to go on 125, which was a Wednesday. And there was some bad winter weather. I was driving on 77, and it was like, ooh, horrible. The next day, this Thursday, I was coming back and it was the morning and I was like going back this way, down south. And I got to this place, which I hate now every time I drive by it, which really isn't that often. I don't go there that much, but it's right by Camp Creek, so I always remember. And there's a horrible curve right here. And I say horrible because it's going downhill. And what was happening that day was I was passing a car around here. So I was in the left lane, and right around here, I went back over into the right lane because that's what you do when you're done passing somebody. But there was some black ice right here, and naturally, there's a centrifugal force. And what this force is a force that pushes an object away from the center of a circular motion. And if you can imagine this is a circle, this is the center, and so this is pointing away. So the centrifugal force was like, hey, how about you kind of just almost go off this cliff? That's what it was saying. It's like going on, it's always the outside of the curve, if you can see. It pointed that way. So I was going here, and then it was like trying to make me go this way. So already I was moving to the I was turning the wheel to the right anyways because I was going back over in the right lane, but there was also a curve to the right. So that combined with the centrifugal force and the black ice, all three of those things, um, which I could not see the ice, and that I was going downhill, that was a combo of disaster. Um, so this is what it looks like at that point. So if you can imagine, I was right here and I was going like that, just turning, going back over into this lane. But what's right here, not that good. This is what it would have looked like that day. This is not a picture from that day. This is street view from 2025, but same idea. There, it was like winter conditions. So this is the exact location. And over here, you might not be able to see, but there's a drop off right there. So I slid and I almost hit this guardrail, and I would have gone over that edge if that happened. I'm pretty sure because my car was kind of a high car at that time. And so I'm glad I didn't, especially since there's a story of in the 90s, a tractor trailer went over this thing, and it's a farm down there. I can kind of see right here, but it's a farm, and the guy on the tractor trailer, he was fine, but he just went like and just drove down into that field basically, or went off and so centrifugal force, that's what that does. It says it tries to push you to the outside of a curve. Now, how can that apply for wind? Well, in the upper levels of the atmosphere, we have situations like this, and we already looked at that. There's ridges and troughs, and there are certain patterns in the wind flow that exist. So you can see in a ridge, these are the forces that are at play. Pressure gradient force up. Now, why is that? Well, because it's going to go from higher to lower um, pressure and also high to low heights as well, because those are related to each other. So it's not the same thing. It's definitely not. But I'm really going to refer to it as higher heights to lower heights in this situation because when we're in the upper levels of the atmosphere, the maps that we look at are of um, everywhere is the same pressure, but there's different heights on the map. When we're at the surface instead, it's um, the same height everywhere, but different pressures on the map. So in this case, something like this would be on possibly a 300 millibar map. And if I say that, what does that mean? It means everywhere on that map is 300 millibar pressure, everywhere. But there are differing heights at which that millibar pressure exists. So that makes it, we talked about in the last video, it makes it interesting to look at in a two-dimensional map. But that what you have to just imagine is that the map is like a paper that's like this. So you have to just say, okay, where it's a higher number, that's a higher height where that pressure is. And if you remember, um, towards the equator, you have the higher heights, and more north, you have the lower heights. So the pressure gradient force, that's why it points up because it's saying we're going to go from the higher heights to the lower heights. And review in the last video of why that happens, but that's why it also points up for the trough too. Because once again, even though it's a trough, still there's lower heights over here. So um we have the Coriolis effect down. And why? Because it acts in opposition of the pressure gradient force. But the centrifugal force is what will change depending on if it's a ridge or a trough. And imagine I'm driving on this thing. Ooh, go to the outside of the curve. Ooh, go to the outside of the curve. It points into the place where it's the outside of the curve. So here, the outside of the curve is there. Here, it's there. So it would point up or down. And that is going to affect wind speed. If it's in the same direction as the pressure gradient force, we'll have faster winds at a ridge. Um, so that's because they're in the same direction. But if it's in the same direction as the Coriolis force and it's an opposition of pressure gradient force, that's why we'd have slower winds at a trough. Now, there's going to be something that happens in between those points. That's convergence and divergence. It can't just what would happen if it goes from fast to slow or slow to fast? Convergence, that's going to be if you're going from faster winds to slower. And that's like a traffic jam. So it's like or you can think of it as you're behind a slow grandma, so the grandma's just like, "Whoa, just going slow." And then you have the mad guy like he goes close to he's going faster, and then he comes up on the slow grandma, slower wind. It's like, oh, dang it. And you can imagine their two vehicles would converge. Maybe he crashes into the back of the grandma because he's not paying attention. Woo! Um, so that's convergence. You can imagine that the grandma's just going so slow, and then this guy's going faster. Converges. That's what converge means. Is two things would go like that. Now that's convergence, right? Divergence is the opposite, as if instead the faster guy's ahead of the grandma. So the faster you have faster winds ahead of slower winds. So we're going from slow to fast. You could think about it that way too. So the grandma's behind the slow guy. So they diverge because he's going faster. So they're going to pull apart. So Sonny, wait up. Oh, like maybe it's the grandson, leading the way to maybe the family reunion, but the grandma's not going to go that fast. Hey, wait up. And they separate. That's divergence. And that makes sense because that's what uh, to diverge, that's what that means. Now, what is going to happen at these places of convergence and divergence? Now, once again, keep in mind, convergence and divergence don't happen right at the ridge and right at the trough. They happen in between them. That's something to think of. You'd want to make sure that you could draw something like this, by the way. But what would happen at those exact points? Ooh, important things, important things. So let's first talk about what would happen at divergence. Um, so this is like, you know, you're at a red light and then there's a car speeding up from the red light. Or we'll just really look at this example. So once again, divergence is um, that you have the fast guy in front and the grandma's left behind. Oh, wait up. It's separated. So fast wins ahead of slow wins. Fast grandson ahead of the grandma. Void is created. Okay, so they're separated. So, oh, what's there now? Is there just empty space there? There's no wind in between them. Okay, well, air has to replace that. And how's that going to happen? Air is going to rise to replace that. So it's going, and this is talking about the upper levels. Okay, so once again, this is the upper levels of the atmosphere. So air from below is going to rise to fill that gap. And um, if that's going to happen, now there's going to be less mass at the surface because that air has left the surface. It's risen to fill that gap between the two people. And if there's less mass, pressure decreases. So less mass means a pressure decrease. And pressure decrease, we might know that that could mean certain things for weather. We'll talk more about that later. But that's why this matters. Convergence is the other way around, is a yellow light would be something like a yellow light crash. It's like um a slow grandma, but then there's a fast guy behind. What? Oh, crashes into the back of the grandma. They converge. And what's going to happen there? Now air is going to be like pushed down. It's like, ooh, because it collision or whatever. And so now there's going to be more mass added to the surface, so pressure increases. So that means that with convergence, there's going to be a pressure increase, divergence, a pressure decrease. Um, now, if you can see this text down here, it's pretty small, but um, at the surface, if we have a high pressure system, there's going to be divergence. And at low, there's going to be convergence. And that's because it's different. this text is talking about what happens at the upper levels of atmosphere. The surface is going to be different because if you think about it, if there's divergence at the surface, can air rise? There's nothing there. There's nothing. We're at the surface. So instead, air would have to sink down to fill that gap if we're at the surface. Um, and when we have that would mean there's added mass, which is a pressure uh increase, which would mean high pressure, right? So then on the contrary, if we have convergence at the surface, that's going to make that will cause there to be less mass because if it converges, then it's going to have to rise or just go away, and that's going to cause a pressure decrease. So you can think about it in both ways. They're basically these two things are actually saying the same thing, but it's just talking about point of view, like surface or upper levels. And so what is sinking to one point of view would be rising to the other, if that makes sense. But you can really just think about it in one way and then just think about what would happen for the other. Um, we also have other things called difluence and confluence, and they conf or di difluence is just basically directional divergence. So that is still going to be divergence, but divergence in directions. So you can see that winds would be moving apart in different directions. So that's going to be more like this, like opening in a V, and it would still create a void, and air is going to rise if it occurs at the upper levels to fill that void, and air will sink at the surface because once again, if we have a gap created at the surface, air can't rise to fill that surface because if we're at the surface, there's just a ground below. It can't rise because we're at the ground already. So only air could go down to fill that. So it would sink at the surface to fill that gap. Confluence is directional convergence. So it's going to be more like a upside down V going together. Winds moving together from different directions. And both of these, they still act the same way as convergence and divergence did, but the only difference is that it's just coming or going from different directions. So in this case, if we're having something like this at the upper levels, air will sink. If this is happening at the surface, air is going to rise because it can't sink. If you think about it, it can't sink because there's just a ground below. Not possible. So air is only going to move where it can, right? All right, so that's going to be it for this video. Thank you for watching.